Find the absolute maximum and absolute minimum for the function 1/2 x squared minus arctangent of x squared minus 1 between -2 and +2. And there's a note, arctangent of 3 is approximately 5/4. Of course, that doesn't surprise us. I'm sure we've all memorized values of arctangent. And if you look at arctangent of 3, as you'll probably recall, it starts as 1.2490. So 5/4 is a pretty reasonable approximation. So, all right. Now, what type of problem is this? Now, one of the things we have to learn when we're doing math is to say, okay, look, I have all these cool tools available to me, but I also need to make sure I know when to use the tools. What's sort of some key words here in this problem that we should look for? Yeah. This is problem, when you see that word absolute, that's sort of an indicator that this is a very particular type of problem where you're going to use a very particular technique. Now, the technique you use when you're dealing with an absolute, and you're probably thinking, well, only the cis deals in absolutes. But no, we do it in calculus as well. So here, what's the procedure? Well, for this, we are making a list. So the absolute max and min is the one where you say, I'm going to make a list of where things could happen, and then I'm going to see which points on my list give me the right values. So this is the making a list, and then we're going to find out which points are nice. So when you're making a list, what are you making a list of? Well, your list is your critical points, where maxes and mins could occur. So you should always start your list with the easy ones. Which points are really easy to throw into the list? The endpoints. And the nice thing about putting the endpoints is, you know they have to be there, and now it feels like I'm making progress. Yes. So it's always good to start with the endpoints. Now the other points are related to the derivative. So the next thing is take the derivative. So what is the derivative of 1/2 x squared? X minus derivative of arctangent of x squared minus 1. 1 over 1 plus x squared minus 1 squared. Remember arctangent, the derivative of that is 1 over 1 plus whatever's on the inside squared. Anything else? Times 2x. All right. Well, let's see, what can we do? What can we do? Well, we can work on this denominator. If we expand it out, that would be 1 plus x to the 4th minus 2x squared plus 1. Or we could really say this is x to the 4th minus 2x squared plus 2. So currently we have x minus 2x over x to the 4th minus 2x squared plus 2. Now, I should have paused and said, is this derivative ever undefined? The only thing we might be nervous about is, could we divide by 0? Could we divide by 0? No. So the arctangent is 1 plus a square of something. So it's always going to be at least 1 in the denominator, which means we don't have to worry about division by 0. So the only thing left on our list of critical points is where the derivative equals 0. So that's why we want to sort of manipulate things to get it to something where we can work with. Now, if we get this all over one denominator, so we multiply the first term by x to the 4th minus 2x squared plus 2 over x to the 4th times 2x squared plus 2. Then we'll get something that we can, like this. So this is putting everything over one common denominator. All right. So what do we have? Well, that's x to the 5th minus 2x cubed plus 2x, subtract 2x, over x to the 4th minus 2x squared plus 2. And now we say, this is nice. What happens? 2x's cancel. And we can even go a little bit further. What do we have? Well, we can factor out an x cubed on top. X cubed times x squared minus 2 over x to the 4th minus 2x squared plus 2. Now remember, we're saying that equal to 0. Because we're looking for the critical points. We already talked about the fact that the derivative is never undefined, So the only thing left is the derivative equals 0. So what are some values where this is 0? 0. So really, we don't worry about the denominator. It's the numerator that's going to give it to us. So x equals 0 works. Is there anything else? Yeah, look at the other terms. X squared minus 2 equals 0. Well, that's x squared equals 2, which is really plus or minus square root of 2. All right. So there's our list. And the nice thing is that the maximum and minimum value for the function on this closed interval is going to happen somewhere at one of these points. But we're not done yet. What comes next? Yeah, got to plug each one of these points back into our original function. So now comes the time when we patiently work through and evaluate each point. F at negative 2. Well, that's 1/2 times negative 2 squared minus arctangent of negative 2 squared, which is 4, minus 1 is 3. Of course, if I square negative 2, that's 4. So this is 2 minus arctangent of 3. Now, we can use the fact that we know roughly what arctangent of 3 is just to help us understand what would be. So since arctangent of 3 is about 5/4, if I take 2 subtract 5/4, that's approximately what this value is. 2 subtract 5/4, what is that? 3/4. All right. Now that's f of negative 2. Now, how about f of 2? Well, let's cheat a little bit. By cheating, meaning use mathematical knowledge. Look at the function we have here. This function is not very odd. What is it? It's an even function. So this function, f of x, is even. Now what that means, recall, that says that it has symmetry. I don't know exactly what it looks like, but whatever it does on one side, it flips straight across and does the same thing on the other side. So even functions when you have that symmetry. So whatever you get when you plug in positive 2 is the same as when you plug in negative 2. And since we already plugged in negative 2, we know that this is going to be about the same. It's going to be 3/4. In fact, it's 2 minus arctangent of 3. Okay, how about when we plug in 0? What do we get? Well, 1/2 times 0, 0, minus arctangent of negative 1. So what is arctangent of negative 1? How about we start with arctangent of 1? Do we know that? It's pi over 4. What's arctangent of negative 1? It turns out it's negative pi over 4. Now, how do we know that? Well, one thing we know that is arctangent is an odd function. It has this shape. So if I plug in positive 1 and I got pi over 4, if I plug in negative 1, I'll get negative pi over 4 because of the symmetry. So we end up with a positive pi over 4. Okay. How about f of square root of 2? What would that be? Well, 1/2 times square root of 2 squared would be 1/2 times 2, which is 1, minus arctangent square root of 2 squared would be 2 minus 1 is arctangent of 1. So this is 1 minus pi fourths. And again, by symmetry, we'll get 1 minus pi fourths again. So the question is, which number is the largest? We have 3 numbers to choose from. 2 minus arctangent of 3, pi over 4, and 1 minus pi over 4. Well, it might be helpful to think about pi. Pi is 3.1. Okay, that's actually a bad estimation. It goes on, but it's a little over 3. So pi over 4, well, it's like 3 over 4 plus another little piece over 4. So how does pi over 4 compare to 3 over 4? Yeah, so pi over 4, this is actually bigger than 3 over 4, since pi is bigger than 3. Since pi is bigger than 3, pi over 4 is bigger than 3 over 4. Now, that tells us that this pi over 4 is going to beat this value of 2 minus arctangent of 3 because it's about 3 over 4. It's really close to 3 over 4. And pi over 4 gives us a good cushion. How about 1 minus pi over 4? Well, that's going to be below 0.25. So that's going to be smaller. So this is definitely smaller than 0.25. And compare it to these others, that's the smallest. So we get that the absolute max is pi over 4, and the absolute min is 1 minus pi over 4. Now, you might say, well, hold on a second. Is it okay that we had the absolute min occur in 2 different places? Is that okay? Absolutely it's okay. It's perfectly fine to have the absolute minimum occurring multiple times. And that happens a lot. Any function that's periodic will definitely have that happen. So it's just, we want to take the smallest value, no matter how often it shows up. All right, and that's good. I like arctangent problems. Arctangent problems are fun. All right, so on to today's topic. Now, we start by what we talked about last time. So it's a quick refresher. We talked about the following. We said there's this beautiful idea called the extreme value theorem. And the extreme value theorem says if you have a nice function, and nice means continuous, on a closed interval, so we start at some number a, go up to some number b, and stop. And we include the endpoints. So if we have a nice function on a closed interval, bounded, then that has to attain a maximum value. It has to attain a minimum value. That's why the procedure we just did works, because we know there's a max and a min. And once you know that there exists one, it's just a matter of saying, okay, all we have to do is find it. And how do we find it? We look at the critical points. Where is the derivative 0? Where is the derivative undefined? Or where is the boundary? Okay. And then we finally made the observation, if we're at a max or a min, we have to be at a critical point. Now today, we're going to talk about Rolle's theorem. So here's the statement. These are the assumptions. This is not the conclusion. So Rolle's theorem says, suppose you have an additional assumption. So remember the extreme value theorem said you're continuous. So Rolle's theorem says, I want to have 2 more conditions. Namely, that my function agrees at my endpoint. So f of a is equal to f of b. And the other thing is not only do I want my function to be continuous, I also want it to have derivatives. So I can differentiate. So if we add these extra conditions in, then here's the conclusion. I have to have a place where the derivative is equal to 0. So there must be a time, strictly between a and b, there must be some time when the derivative has to equal 0. Must occur. Now, I'm going to walk through a sketch of the proof. You don't have to know the sketch of the proof, but if you're interested in why is this true, here's the reasoning. So the key thing is we build off of the extreme value theorem. The extreme value theorem says we know there's an absolute max and we know there's an absolute min. So we say, all right, let's find them. Now, one possibility is that the absolute max and the absolute mins are at the endpoints themselves. So what would happen if my absolute max and absolute min were at my endpoints? What would have to be true about my function? What would it look like? If my absolute max and absolute mins are at my endpoints, that means I cannot move up and down in between. So my function is flat. Well, we know how to take the derivative of a flat thing. The derivative of a flat thing is 0. So if the absolute max and absolute mins are at the endpoints, life is good. It's a true statement. What if it's not? Then life is even better. Why? Okay, so find that absolute max. And we look at that and we say, hey, that absolute max has to be a critical point. But what kind of critical point can we have? It can't be the point where we're at a boundary because we're in the middle. It can't be a place where the derivative is undefined because we said the function is always defined. The derivative is always there. So by process of elimination, it has to be a place where the derivative is equal to 0. And so that's Rolle's theorem. All right. So we're going to talk about that, and we'll verify it for some simple cases. But that's the proof. So we're going to start by saying, why do we need these conditions? So when we talk about the three conditions, we're talking about these three conditions. The endpoints match, we're continuous, and we're differentiable. Okay. So we'll go through and say, what would happen if we dropped some conditions? So let's first drop the condition, what if we have f of a not equal to f of b? So the picture here is I have a and I have b, but these don't match. So in other words, when I plug a into my function, I get a value, but I plug b into my function, I get a different value. Can we make a nice continuous function that joins these 2 points together, but never has a derivative of 0? Yeah. And don't try to be clever. Be unclever. What's an unclever way to do it? Yeah, you draw a line. You'll notice there's no place where the derivative is 0 in between. So we do need to make sure, if we're looking for a derivative equals 0, we have to have those endpoints have to match. No choice. They have to match. Okay, that was the first condition. Now the second condition was the following. It said, hey, f has to be continuous if I'm between a and b. Now let's actually be really strict on ourselves and say, suppose we assume f of a equals f of b and f is differentiable. Now you might say, Steve, you're going to run into trouble. Because you know if you're differentiable, what has to be true? You have to be continuous. But we can make a little observation. I only have to be differentiable away from the endpoints. So I can drop the continuous assumption and say the following works. So f not continuous. It's going to look very familiar. I'm going to just change this picture. Now, notice that f of a equals f of b. It's differentiable between a and b because it's a straight line between a and b. But is the derivative ever equal to 0? And the answer is no. There's no place where the derivative equals 0. So you do need to have that assumption about continuity. Okay, so what if we say you are continuous, f of a does equal f of b, do we need to have that differentiable? Well, okay, so we have to assume f not differentiable. Is there a function we can think of? We'll start a new picture. I want to go between a and b, and I want to get there, but I never want to have a flat line. Is there anything that we've drawn that has that type of behavior? Like the absolute value does that, yeah. So you can do something, you can go up or down. I'll go up just because of space. That gets between my two endpoints. And it's continuous, but you'll notice there's a little problem here. There's this peak. It's not differentiable at this point. So all three of these conditions are very important. If you drop any one of those three conditions, it's no longer a true statement. But we've already seen the proof, and so we know that as long as we have those three, then it works out. So now we'll do an example, verification. Verify Rolle's theorem for the function f of x, which is equal to x cubed minus 7x. And they gave us a picture. Well, that's very nice of them to give us a picture like that. And we want to do it the interval from -3 to +1. And the way that we're going to verify it is we're going to say, there must be some point C where the derivative is equal to 0, because that's the claim. Now you're probably thinking, hey, good news, Steve. It's right there. Well, okay, yeah, we can see it from the picture, but we're going to find it. We're going to do it the proper way. Now, we should, of course, verify a couple of things. Is the function continuous? Yes. Okay, good. Do the endpoints match? Let's just verify. The picture says they do. Let's see if they actually do. Negative 3 cubed? It'll be negative 27, because the negative cube will be a negative. Then we have minus 7 times minus 3, which actually be plus 21. So that's negative 6. F of 1, well, that's one's a little bit easier to do. That's 1 minus 7, which is negative 6. So that tells us that it is true that the endpoints match. We did check that it's continuous. Is it differentiable? Well, let's find out. What is the derivative? 3x squared minus 7. We found a derivative, and therefore, it is differentiable. All right, good. So, what's the next thing? Well, the Rolle's theorem claims that there's some place where the derivative equals 0. So we set this equal to 0. And this becomes 3x squared equals 7, or x squared equals 7/3. So what is x? Plus or minus the square root of 7/3. Now, remember the claim. Now, I don't know exactly what the square root of 7/3 is, but I do know one thing. It's bigger than 1, because 7/3 is bigger than 1. So, the claim, remember, is that there's some point in between. Is either one of these 2 points in between negative 3 and positive 1? Yeah, the negative square root of 7/3. So that's what C is. This point, it would be somewhere on the other end over here where it dips down. So this is our desired C. So we found our C that we were looking for. Now the Rolle's theorem has, you can think of it as either a nice generalization or a special case. It turns out they're both equivalent to each other. So there's something called the mean value theorem. And then the mean value theorem says, let's try to drop that assumption that we have. So Rolle's theorem says, I need the endpoints to match. The mean value theorem says, let's take that assumption out. Let's get rid of it. What can we say? Well, it says the following. So we have this nice function. It's continuous from A to B, including the endpoints, and it's differentiable between A and B. Then what has to be true is that there's some point in the middle, so some point away from the endpoints, where the derivative at that point, f prime of C, is equal to f of B minus f of A over B minus A. If you think about Rolle's theorem for a minute, remember what was one of our assumptions with Rolle's theorem that isn't being assumed here? F of B equals f of A. What happens when you plug in f of B equals f of A? You get 0. So you can think of Rolle's theorem as being a special case of when f of B equals f of A. Now the way to read that statement is you can say, well, f prime of C is a rate of change. It's an instantaneous rate of change. Namely, how fast are you going at a particular moment at time? F of B minus f of A over B minus A, that takes us back to our very first session. It's just a few weeks ago, but it feels like longer. That's the average rate of change between A and B. So what we're saying is that if we have a reasonable function, that the average rate of change between our endpoints is going to match the instantaneous rate of change at some point between our endpoints. So there's an analogy with driving, and people believe this, which says the following. Suppose you're on a trip. Maybe you're driving down to Des Moines. And you're driving down, and at the end of your trip, you look down, and you say, I averaged 70 miles per hour on my trip down to Des Moines. What has to be true? Well, what has to be true is that at some point in time, you were going exactly 70 miles per hour. Now, it doesn't mean you're going 70 miles per hour the whole way. Sometimes you might be going a little bit faster, sometimes a little bit slower. But there was some moment on your trip, possibly multiple times, but at least one, where you were going exactly 70 miles per hour. So law enforcement, by the way, knows calculus, and they've used this to their advantage. So there were some parts in the country where they could see a fairly large part of the road, and they would see cars driving, and they'd have a stopwatch, and they'd start the stopwatch when a car passed a certain point, and they'd stop it after it passed another set point. And they'd see, okay, how long did it take? Because what they were doing was they were measuring your average rate of speed. And they were able to say, well, look, we knew what your average rate of speed was, so we know that at some point you're going at least that fast. And therefore, by calculus, you could get a speeding ticket. So, now you're like, I don't like calculus that much anymore. Okay. Now, we talked about how Rolle's theorem follows from the mean value theorem. It turns out the mean value theorem also comes from Rolle's theorem. So we don't actually have to prove anything new. So you might say, but how is that possible? So the way to think about it is that you take Rolle's theorem and you tilt it. So we're going to temporarily construct this new function called g of x, which is f of x minus f of b minus f of a over b minus a times x minus a. Not the most exciting function, but bear with me for a moment. Let's test a couple of things. What can we say about g of a? Well, what happens when we plug in g of a? The first term gives us f of a. What happens to the second term? Because of the x minus a minus a is 0, it goes away. How about g of b? Well, we get f of b plus f of b minus f of a over b minus a times b minus a. B minus a's cancel, and my inability to copy makes me nervous. That's a minus, not a plus. Then what happens? The f of b's cancel. You're left with f of a. So g of a is equal to g of b. By Rolle's theorem, and we can say Rolle's theorem applies because this is a continuous function. We're making that assumption. And this is a line. And lines are very continuous. So if we put these two functions together, we're still continuous. Similar, this is a differentiable function by our assumption, and lines are differentiable. When we put differentiable functions together, they're still differentiable. So we know that there's some point where 0 is equal to the derivative, g prime of c. But, wait a second, what is g prime of x? Work it out. It is f prime of x. And what do we get when we take the derivative of this part? Well, the answer is the derivative of this piece is 1. So we end up with f prime of x, whoops, not equals. There's a minus f of b minus f of a over b minus a. So if g prime of c equals 0, that says that f prime of c minus f of b minus f of a equals 0, or f prime of c equals f of b minus f of a over b minus a. Okay, so that's how you can prove Rolle's theorem, the mean value theorem using Rolle's theorem. So here's an example. So I have this function. I start here at a, f of a, and then here at b, f of b, and I'm moving up and down. You can see there's this dotted line here. The dotted line, that corresponds to the slope going from the point a f of a to b f of b. That is your average rate of change. So you connect the 2 points, the slope of that is your average rate of change. And then you'll see that there's 2 places where we have the tangent lines, which are drawn here in red, are parallel to this dotted line. So where you see these tangent lines parallel to that dotted line, that's where your derivative has to match. So in other words, in this case, we have not 1 point, but actually 2. So we can have multiple times when the derivatives match. So it's not necessary that you just have a single point where it's true. You can have multiple times when things are true. So let's try this out. So verify the mean value theorem for the function h of t equals 2t times 1 plus t squared, where we let t go from 0 to 1. So first off, we have to understand what do we mean by the mean value theorem. What is it saying? Well, the claim for the mean value theorem is that we have h prime of c is equal to h of b minus h of a over b minus a. Now, we were given our function h, and we've been given a and b. So what we need to do is we need to say, let's figure out what should that right-hand side be, and then see is there any value for c where the left-hand side matches up. So we begin by figuring out these values here. So in particular, we want to look at h of 1 minus h of 0 over 1 minus 0. If we plug 1 into the function, what do we get? We'll get 2 over 2, which becomes 1. If we plug 0 in, what do we get? We'll get 0. And lo and behold, that simplifies to 1. So in order to verify the mean value theorem, one thing that we have to do is we have to find any place where the derivative is equal to 1. So to find that, first let's take our derivative, h prime of t. How do we take the derivative of 2t over 1 plus t squared? The quotient rule. So, quotient rule says we take the bottom function and we times that by the derivative of the top. Then we subtract the top function times the derivative of the bottom, which 2t. That's the derivative of 1 plus t squared. And we divide that by the bottom function squared. Okay, so remember, what are we after? We are after some value of t where our derivative doesn't equal 0, it equals the average. So we want to set this equal to 1. So if we can find some t where this is true, then success. All right. Well, I hope we find such a t. That would be great. Cool. So, I would say, I don't like fractions. So let's get rid of the fractions. So we'll multiply both sides by 1 plus t squared squared. So we get 2 plus 2t squared minus 4t squared. That's the numerator. Equals 1 plus t squared squared. Now, this becomes 2 minus 2t squared on the left-hand side. On the right-hand side, that becomes 1 plus 2t squared plus t to the 4th. If we move everything over, we're going to end up with t to the 4th, and then plus 4t squared, because there's a minus 2t squared comes over as a plus 4t squared, and then minus 1 equals 0. All right. Well, what do we do? Now, you're probably thinking, it's a 4th degree, Steve. We don't have a formula for that. But is it really a 4th degree? Yeah, that's a 4. So, but no, I mean, is it really? Well, you can think of this as like t squared squared plus 4 times t squared minus 1 equals 0. So if you think about it as your t squared as being your basic building block, maybe we could call it, say, a squared plus 4a minus 1 equals 0. Now you're like, okay, all right. That we can maybe handle. How do we handle this one? What do? We want to factor, right? Does it factor? No! And what your reaction is probably like, no! That means we can't factor, so what do we have to do? Yeah, see, even if you can't factor, there's always that, backup. Once or twice in your year and a half of calculus, things won't factor. This is one of those occasions. Okay, that's all right. We're ready for it. We knew this day would come. Okay, so what is a? Well, negative b plus or minus the square root, b squared, minus 4ac. So that'll be plus 4 all over 2. Now, if you clean this up, this becomes negative 2 plus or minus the square root of 20. You can think of it as 4 times 5 on the inside. And so you can bring out the square root of 4 as 2 and cancel. So negative 2 plus or minus square root of 5. Now, remember, what is a? A is t squared. Can we have negative 2 minus square root of 5 be something that came from a square? See, negative 2 is negative, and if you subtract square root of 5, it's even more negative. So it's negative, right? That's the point. So no, it can't happen. So that says that t squared has to be negative 2 plus square root of 5. Now you're probably nervous, but we're saying, wait, is that positive? Well, how big is square root of 5? Is it above 2 or below 2? It's above 2. So negative 2 plus square root of 5 is going to be above 0. Now that's t squared. What were we after? We just want the t, because we're after, remember what our goal was, we wanted to find some point, h prime of c, where when we plugged it in, we got 1 out. So we set our derivative equal to 1, and we're solving for it. And so now, to finish it off, what do we need to do to get t? Square root. Now there's a plus or minus, but for us, which one do we need? The plus, because we need to be between 0 and 1. So the final answer is this works. We choose c equals the square root of negative 2 plus square root of 5. Exactly what we would have guessed before we started. No, probably not. But that's why we have math. It's a systematic way to figure out the answer. And so it's good that we have that beautiful system. Okay, well, let's try another one. Find all the points. Well, that means there might be more than one. Find all the points, satisfying the conclusion of the mean value theorem for the following piecewise function, negative 2 less than or equal to x less than or equal to 2. Now, we have a piecewise function. We look at the two pieces. The 3x minus x squared, we're cool with that piece. The x cubed plus 2x squared plus 3x. Again, a beautiful function. But what are we worried about? We're worried about when we bring those two together. Because in order to apply the mean value theorem, what needs to be true? It needs to be continuous and it needs to be differentiable. So we get like a Okay, so let's just check. So we need to check continuity. So the way you check continuity is we see what happens at 0. When we plug 0 in, we'll get 0 minus 0 squared, which is good. And here we'll get 0 plus 0 plus 0, which is 0. So the pieces line up. It's still not enough to be differentiable. So for that, we should take our g prime of x. So the nice thing is we can just take the piecewise. Root of 3x minus x squared. 3 minus 2x. And this is if we're above 0. And we're going to wait before we make a conclusion about 0. Okay. Root of x cubed plus 2x squared plus 3x. 3x squared plus 4x plus 3. And that's if we're less than 0. Now what are we checking? We want to see what happens at 0. When we plug 0 into the top one, we get 3. When we plug into the bottom, we get 3. And it's true that 3 and 3 are the same. Okay, so that means that they match up as well. So it is a continuous and differentiable function. It's continuous and differentiable everywhere. So we can apply the theorem. So now what we want to do is we want to say, all right, what is the ratio, this ratio of the average rate of change? So we're looking at g of 2, subtract g of negative 2, divided by 2, subtract negative 2. Well, if I want to plug 2 in, which rule am I using? The top rule or the bottom rule? I go with the top rule because that's where 2 is greater than or equal to 0. So when I plug 2 in, what do I get? 6 minus 4, which is 2. When I plug in negative 2, which rule am I using? I use the bottom rule because negative 2 is below 0. So I'm going to subtract. Well, let's see what we get. We'd get negative 8 plus 8. And then here it would be negative 6. So I'm going to 8 and my negative 8 cancel, so I end up with 2 subtract negative 6. Downstairs I'm going to end up with 2 plus 2. We put that all together, what do we get? 8/4 or 2. So when we're looking for all the points which satisfy the mean value theorem, now what we're really saying is we're asking the question, when does g prime of x equal 2? In between negative 2 to positive 2. The mean value theorem says it has to happen somewhere between negative 2 and positive 2. So there's our goal. Well, what we do is we just say, look, we have our derivatives, and we set each one equal to 2 and see what happens. So when does 3 minus 2x equal 2? We do a little bit of math. Well, that's what, every day we do a little bit of math. All right. 2x should equal 1, or x equals a half. Well, that looks like it's good because a half is between negative 2 and 2. So 1/2 is one of our points. But remember, it didn't say find a point, it said find all points. Okay, so let's put our answer in a box. 1/2. Maybe there's more. Okay, for the next one. So again, we're taking our derivative equal to 3x squared plus 4x plus 3 equals 2. Well, that becomes 3x squared plus 4x plus 1 equals 0. Now what? Yeah, we try to factor. And you're probably like, wait, don't we need quadratic? No, only if factoring fails. I don't want you to be too discouraged by factoring. It does work in many cases. Does this factor? Yeah. 3x plus 1 and x plus 1. So, when does 3x plus 1 equal 0? Negative 1/3. When does x plus 1 equal 0? Negative 1. And those are also points in our interval. Now, there was one thing that we should point out. We got lucky here that didn't get us into trouble. The point 1/2, we said, yes, it's between negative 2 and 2, but what else was important? It had to be in the range where we were applying the rule. See, the 1/2 came in the range where we were applying the greater than 0 rule. So we got away with it. And these points, negative 1/3, negative 1, had to be between negative 2 and 2, but also had to apply to the range here, where we were below 0. So we were good. So always double check to make sure what's your range. So in this case, we have 3 different points which satisfy the conclusion of the mean value theorem. And I know that there's a quiz problem coming up where you'll get even more than 3 points which satisfy the conclusion of the mean value theorem. It's a beautiful quiz problem. But that goes without saying. All quiz problems are beautiful. All quiz problems are beautiful. So, why do we want the mean value theorem? Well, here's a nice consequence of the mean value theorem, which we're going to use later on. Suppose I know that my function has a derivative of 0. In other words, my function is 0 for all points from A to B. Then the mean value theorem says you have to be constant. The only way you can ever have a function whose derivative is 0 is to have a constant function. Now, there's a question we should ask. Why? So we reason it. So it says here, our derivative is equal to 0. The conclusion is that f of x is always the same value. So think about, okay, if this wasn't true, then there'd have to be some function where I'd have 2 different values. So here's my function, here's a, here's b, and so there's some point in between where I'd have 2 different values. Because if my conclusion doesn't hold, I'm not a constant. But what's true about the average rate of change between those 2 numbers? Because they're not the same number, this average rate of change is not 0. But remember what the mean value theorem says. If you have an average rate of change, somewhere in between there's an instantaneous rate of change which matches it. So that would say that there has to be some point in the middle where the instantaneous rate of change matched the average rate of change. So I don't know where this point is, but I know it exists. So this has to equal an instantaneous rate of change somewhere. But now we have a problem. An instantaneous rate of change which is not 0. But what is our instantaneous rate of change? It's always 0. So that's why it can't happen. Okay, so the only function whose derivative is 0 is a constant function. That's a believable statement. But here's the really nice part. This is why we like this. Suppose we have that two derivatives match. Then it says that those two functions are almost the same. And in fact, the only way they differ is they differ by a constant. So this is kind of nice, because we've talked in the past, we said, hey, if two functions are exactly the same, their derivatives have to match. But now we're saying, okay, suppose we have the knowledge that two derivatives match, what's true about the functions? And it turns out they don't have to be the exact same, but they can't be very different either, because they can only differ by some constant d. Now, if you're wondering how do you prove this, the answer is the proof follows by noting you let h of x equal their difference, f of x minus g of x. And once you do that, apply the previous result, and it follows. So we're going to use this when we get into what's called anti-differentiation. But that doesn't sound very fun. We'll wait until after the next exam to start doing that. But let's do a quick example of how we can use this. So suppose I have some number a greater than 0. And suppose I have two functions, f of x equals log x and g of x equals log of a times x. So let's show that f prime of x equals g prime of x. So let's just quickly do that. The derivative of log x, what is that? 1 over x, because log x is one of our functions we know. Derivative of g prime of x. By the chain rule, 1 over the inside times the derivative of the inside. But now the a's cancel, we get 1 over x. And these match. So that tells us that the derivatives have to match, which tells us the following, that g of x has to equal f of x plus some constant d. Or if you like, log of ax has to equal log of x plus some value d. Now that has to be true for every value of x. So let's pick a nice value of x. What's a convenient value for x? Well, 0 is not a convenient value for log. What's another number? Y. So pick x equal 1. Since you know this is true for all x, we get that log of a equals log of 1 plus d, which says that d is log of a. And so the conclusion is log of ax has to equal log of x plus log of a. And that's one of the properties of logarithms. So you can actually establish properties of logarithms through this method of calculus. Of course, it's not the easiest way, but it can be done. And that's it for today.